So overall, uh, this course is about multivariable calculus, and I kind of wanted to just take a moment to provide some motivation. Now, we know that calculus is a math where we're interested.
It's 17 hours.
Thank you. Where we're interested, for whatever reason, in limits, derivatives, and integrals, right? Integrals represent physical quantities like area, and distance traveled, and derivatives are really important because they tell us about rate of change, and limits allow us to make predictions, right? So we kind of have an idea of, we've been studying calculus for at least a year now, but whenever we studied calculus, we were only concerned about functions that depended on one variable. This semester, we are incorporating many variables, right? So that's how we get multivariable calculus. And let's look at the notation for functions of many variables. So I've got an example here, and this is an example which some people may, maybe you're familiar with it, but definitely you can understand this idea. Suppose you're taking out a loan, or you're going to give someone a loan, right? And the question can be, what's the monthly payment amount? Well, the monthly payment amount depends on two variables. Depends on how big the loan is, and it also depends on the interest rate, right? So in order to determine the monthly payment amount, you need to know the loan amount and you need to know the interest rate. So we can take that information and succinctly write it like this. So we'll say M, which is the monthly payment. So M is a function of the loan amount and the interest rate. Okay, so this should be very reminiscent and very similar to before, when we might say y is a function of just x, right? You know how you'd have one input x and then you have an output y, or f of x? Here we're going to have two inputs or three inputs. Okay, so that's the notation that we'll be using. And I just wanted to run through about three different examples of functions, because functions of two variables, because for the beginning of this course, we're going to be focusing on working with functions of two variables. We're going to, of course, handle limits and derivatives and integrals, but first we've got to just get used to what does it mean to have a function of two variables. So let's look at these examples. Okay, the first example I have here is of a weather map. So all of us have seen a weather map, and these lines are indicative of temperature, right? And so these thick lines here are called isotherms. And the way we read this weather map is, we say that the temperature is the same along these thick, heavy lines, right? These isotherms. And if we break down the word, therm here means heat, right? And iso means the same or equal. Like an isosceles triangle has equal sides, iso, equal. So isotherms mean this is where the heat or the temperature is the same. So using this, how is this weather map a function of two variables? Well, the output is going to be the temperature, and the input is going to be location. But the location is in two directions, right? So the location would be north-south and east-west. Do you get the idea here? So you could ask yourself, north-south, which would be going in this direction, versus, and then as well as east and west. I need both of those pieces of information, and then I can give, based on this weather map, an approximation of the temperature at that location. Let's look at our second example. This is an example which is beef. Let me highlight here. This is the example. Beef consumption. So suppose beef consumption was a function of the price of the beef and the household income per year of the consumers, right? So now who might be interested in a function like this? Someone who is selling beef, right? Because you want to know how much can you sell, right? So how much beef will a family consume? And perhaps based on your previous research, right? So perhaps you've been collecting data for years and years and years, and perhaps you found out that depending on the price point, right? So depending on the price point, whether it's $3 a pound, $3.50, $4, $4.50 a pound, and also depending on the household income in thousands of dollars. So here we've got 20,000 all the way up to $100,000 a year. You can determine the amount in pounds of beef consumed by a household, say per week, right? So now we're saying here that C, our consumption, is a function of the price per pound and the household income, right? So C, which is going to be the number of pounds of beef consumption per family, per week, yeah, per household, is a function of household income and the price of beef itself. So this is a chart, and do you see how this is very different? This is in some sense like let me point this out, a three-dimensional chart, because you've got information going, you've got the price, you've got the income, and then you've got the output here in the middle. And this is, add a page below. Okay, contrast this to before, or what we're used to, which would be to just have, say, your input here, and then your output, right? Should have input and output. This is for a function of just one variable. Now, with this function of two variables, in order to give this information numerically, you need to have input, two inputs, and then the output is now going to be in the middle of the chart. Okay, so the last example is an example we've probably been seeing forever. These geometric examples are great for algebraic formulas. Okay, so just think about the volume of a circular cylinder. The volume is a function of two variables, the radius of the base of the cylinder and the height of the cylinder, right? And so we actually have a formula this time around, and it would be pi r squared times the height. Okay? Now, we have an idea of, and of course you can think of lots of times, functions depend not just on two variables, not on three variables, infinitely many variables, but in order to make it tractable for studying, we just focus on 2 or 3 or maybe 10, or if you've got a big spreadsheet, you might focus on 100 variables, right? So, and that's why we're getting to big data, right? Big data means you've got a whole bunch of data points and you're considering a whole bunch of variables, right? For us, we're just focusing in the beginning of the semester on functions of two variables. And now that we've seen the motivation for functions of two variables, let's look at how do we graph functions of two variables, okay? And this is going to involve a tour of 3D space. So this D here stands for dimension or dimensional, three-dimensional space. Why will we need 3 dimensions? Look back here. We will have 2 inputs, so we need a dimension that's going to keep track of each input, and we need a dimension for the output, right? So notice when we had 2-dimensional, this is for 2D, we just needed an x-axis and a y-axis, right? X-axis is your input, y-axis is the output. Now that we've got 2 inputs and an output, we're going to need 3 dimensions. And so let's get to that. That's where we'll get to that here. So we'll do a short little introduction. Then we'll talk about graphing points in 3D space. Then graphing equations in 3D space. And the last thing we'll finish out with is distance in 3D space. Okay. And now, I think what I'm going to do just here is just as a reminder, what did we do for 2D space? Do you remember what we did for 2D space? Well, for 2D space, we typically had x and y, and we had the positive values over here for x, and we had negative values over here to the left. And y, positive values we usually put at the top, negative values we usually put at the bottom. Right, and if we had a point, say 3, 2, that meant 3 units to the right and 2 units up. So we would move 1, 2, 3 to the right and 2 units up. Bam, we would plot a point. Okay, so a point back in 2D space needed 2 coordinates, one for the input, one for the output. Okay, and then we had equations in 2D space. For example, we would say, what does it look like to graph y equals x squared? What does the graph of y equals x squared look like? Well, we said that means you want all points x comma y, where y is actually x squared. And so then we would say, well, now what if our input is 0? Then we would have 0 comma 0 squared. Okay, so that'd be 0. What if our input is 1? 1 comma 1 squared would give us 1 comma 1. Or it could be negative 1, right? Negative 1 comma 1. And in this way, we'd plot out, and then we figured, oh, okay, that's a parabola. Remember? Right? So we would say the graph of this function looks like that, and here's how we would do it. And then we got more sophisticated, and we learned about translating graphs and stretching and scaling, right? And shifting up and shifting down, shifting left, shifting right. And distance in 3D space. So what was the distance between 2 points? If this point was A comma B, and this point down here was C comma D, how did we determine the distance between the 2 points? Here's how. We said, let's use a Pythagorean theorem. We know that we can create a right triangle, okay? And then the distance is going to be the length of the hypotenuse of that right triangle. And so we said we'll end up with our distance equal to the square root of a minus c squared plus b minus d squared. So we'll have analogous versions of graphing points in 3D space, graphing equations in 3D space, and computing distance in 3D space. Okay? All right, let's get started. Okay, so what does 3D space look like? Okay, so here we're going to start off with an origin. And you start off with your origin. We can label that O. And we have the x-axis, which is coming out. Now I'm going to draw dotted lines to indicate that it's those are negative values. So here are positive values of x, and back here are negative values of x. So we've got the x-axis, right? X-axis is keeping track of the first coordinate. Then we've got the y-axis, which is going left to right. Here are positive y values and negative y values. And then we need a third dimension, and that is the z-axis. And so the z is keeping track of the up and down. And so positive values up here, negative values down here. So this is, and let me show you kind of one way to emphasize that this is x, this is y, and this is the z, the positive z-axis. Okay, now here, let's see here. Our coordinate axes are the x-axis, the y-axis, and the z-axis. Okay, so we've got 3 coordinate axes. The x-axis direction keeps track of forward and backwards. Okay, so let's think of x keeps track of forward versus backwards. Forward versus backwards. The y-axis keeps track of left versus right. Or we should say right
It's
versus left.
17:15.
Thank you. Right versus left. And then the z-axis keeps track of top versus bottom. Forward, backwards, right, left, above, below, I think is versus below. And everything is with respect to the origin, right? So you start at the origin, and then, so let me show you, we can show you how to plot a point. Suppose I wanted to plot the point 1, 2, 3. Okay, so this is to plot 1, 2, 3. Now 1 is my x coordinate, 2 is my y coordinate, and 3 is my z coordinate. So that means that I need to move forward 1 unit. So I'm going to do it in pink here. So I start at the origin, starting at the origin, move forward 1 unit. Okay. Now I need to move right 2 units. Okay, so do you see how over these are the units? So that's moving right, this is moving left, right? So left is going to be negative. So I'm going to move right 2 units. You see? And then lastly, I need to move up 3 units. So I need to move up 1, 2, 3. So 3 units. Now do you see if I move up from here, that means I'm moving. So imagine this is right, kind of like a column. Now I'm moving up 3 units, 1, 2, 3. This is my final, this is where I plot. That is the point 1, 2, 3. Does that make sense? Okay, so remember how it was back in 2 space. So back in 2 space, for instance, if you were plot back in 2 space, x kept track of right versus left, and y kept track of above versus below. Right? And this is all with respect to the origin O. So now what we're doing is we're adding a third dimension, and we're not only looking at right versus left, above versus below, we're looking at in front of versus behind. Okay? Forwards versus backwards. All right. Now, I want to tell you that there are a couple of different ways. So when we are writing, in this course, I will typically draw. In this course, I will draw the x. I'll start out here. Well, I can tell you. Let me show you what I'll do. So I will typically have, I'll draw something like that to be my x-axis. And then I'll draw something straight like this to be my y-axis. And then I will draw a z-axis coming up top out of it. Okay? And then it can be down here. Does that make sense? However, so this is with my x, my y, and then I'll put an arrow to indicate the positive, right? So this is positive, positive, and then z, positive. Some places, however, it just depends on the context, will have, this is their base. So it'll be, so here's the x, and then they'll do y like that, and then they'll have z coming up straight ahead. Okay, so it's like x here, y here, and z here. It all depends on your orientation. So here's plus, 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 right? It's like it just depends on how, your point of view, your perspective. Now, we have a little thing called the right-hand rule, which determines the direction of the z-axis. Because imagine if you've got your x-axis over here and your y-axis right here, and your z-axis is like that, You've got to know where's your positive z-axis, what's your negative z-axis, right? Well, here's how you determine the direction of the z-axis. So you follow the right-hand rule. So the direction of the z-axis is determined by the right-hand rule. If you curl the fingers of your right hand around the z-axis in the direction of a 90-degree counterclockwise rotation from the positive x-axis to the positive y-axis, your thumb points in the positive direction of the z-axis. Okay, so the idea is, imagine your wrist is at the positive y-axis and put your fingertips facing the positive x-axis, and wherever your thumb points naturally is the direction of the z-axis. Okay, the main idea is that you just want the x-axis and the y-axis to be perpendicular to each other. Okay, and you want the z-axis to be perpendicular to the xy plane. Do you notice that if we look at this plane here, if we look at this 3D space, we've got a plane. And so if you kind of tilt your head, I'm going to draw the parabola. So the parabola that we had before, okay, do you see? If you tilt your head a little bit, you can perhaps see this parabola here. That parabola corresponds to this parabola here. This is 2D now, but in 3D land, it's now flat. Okay? But we could draw that parabola higher up, but then we would have a different z value. Okay, so let's in fact get a little bit about that. So the coordinate planes, what are the coordinate planes? We know the coordinate axes are x, y, and z, but you've got 3 coordinate planes. You've got the xy plane, you've got the xz plane, and you've got the yz plane. Okay, so here's x, here's y, and here's z. And sometimes what I'll do is I will actually not draw in the negative parts. The xy plane is, I'm going to fill this in with, the xy plane is this plane right here. That's the xy plane. So let's see here. Let's try to draw that. XY plane looks like you've got y going this way in this direction and the x going this direction. Okay. The XZ plane, let me use a different color. The XZ plane is like this. So can you see this? And it's like going up and down. Okay, so let's draw it like here. The XZ plane, a way to see it is to draw it kind of like that. So here, the Z is going up and down, and X is going forwards and backwards. And then the last plane we have is the YZ plane. So the YZ plane is like this. And so Y is going left and right, and Z is going up and down. And so if I'm here, if that makes sense, like that. And so we will practice. Of course, you can kind of get an idea of the benefit of being able to graph these things with Mathematica. because we're able to draw and represent our pictures clearer if we're using technology. But so now imagine if when you uh, when you look at the intersection of all three planes, you get the origin. So now imagine you've got your XY plane, and on top of it, you're adding your YZ plane. Okay, so you've got your YZ plane, and then you're going to add your XZ plane. Do you see? So do you see how? Where do they all meet? They all meet at the origin. Okay. Also, another thing to note is that these three planes create octants. So just like, let me add a page above. So just like in the XY plane, so this is in 2D. So in 2D, we had X and we had Y. So we have the X-axis and the Y-axis. And based on the X-axis and the Y-axis, we had quadrants. So this was quadrant 1, this was quadrant 2, quadrant 3, quadrant 4. Right, so this was quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And quadrant 1 consisted of the points XY, the set of points XY, where X is greater than or equal to 0, and Y is greater than or equal to 0. Right, so this was where points all of the coordinates were positive. Well, now we've got 8 different regions. And let me see how to kind of draw this. Okay, so it'd be like, imagine, okay, I think I'm gonna try to do this. Okay, so you've got this little, imagine you've got this box here, then you've got this box back here. Right, and now this, you're doing this 8 times. Well, this is not that good. Okay, so what I want to, it might be better, makes more sense to take all of this and divide it into 8. Because you've got your planes, right? So this plane right here is the XZ plane. This plane is the YZ plane. And then this plane is the XY plane, right? Remember that? So all these planes are intersecting, and the quadrant or the octant, so now we've got 8 octants, and there's only one octant that people refer to. You don't label all 8 because there isn't really a natural way to do that. So you just say the first octant is the octant where the X, Y, and Z are all positive. Okay, so the coordinates X, Y, and Z. So that would correspond to this octant, this little cube right here. Okay, because keep in mind, X is coming out here, Y is coming out here, and Z is coming up top here. So if you've got points that are where the X, the Y, and the Z are all bigger than or equal to 0, then that point is in the first octant. Okay, so graphing points in 3D space. We specify a point in 3D space by giving its coordinates with respect to the 3 axes. Okay, so for example, we already did an example of graphing. We did an example of showing how to graph. I think I erased it. Yeah, I erased it. So let's do, so let's plot the points 1, 2, 3, and 0.
It's 1730.
Thank you. 0, 0, -1. Okay. So I'm setting up my axes. So this is X, this is Y, this is Z. Okay, 1, 2, 3. So remember, this X coordinate tells me to move forward 1 unit. The Y coordinate value tells me to move to the right 2 units, right? So it's like 1, 2. 2 units to the right. And then this tells me to move 3 units up. So now I move up 1, up 2, up 3. And that is my point 1, 2, 3. Let's do this point here, which is 0, 0, -1. Okay. Well, I move 0 units forward. So what does it mean to move 0 units forward? That means I'm still right here. I move 0 units right. So I'm still right here. And this means I move down 1 unit. So I'm going to be down here. So this point is on the z-axis. So this is a point that is on the z-axis, okay? Something that is important when you are graphing points in 3D space is to discuss the projection of the point onto the different planes. So remember, how many coordinate planes do we have? We have 3 coordinate planes. So the 3 planes in 3D space, remember they are XY plane, the XZ plane, and the YZ plane. So let's do an example where we project 1, 2, 3. We can use our same point from before, the point 1, 2, 3, onto the XY plane. Okay. So here's X, here's Y, here's Z. And we said that this point 1, 2, 3 means move forward 1, to the right 2, and then up 1, 2, 3, up 3. Okay, so this is our point. And now if I'm going to project onto the XY plane, I need to remember, what is the XY plane? The XY plane was this plane here. Okay, so that's the XY plane. So now what did I do? I moved up 1, I moved forward 2, and then I moved up 3. So this was 1 unit forward, 2 units to the right, and then 3 units up, right? So if I project this point onto the XY plane, I'm looking at this point right here. Because you think of projecting, like imagine if you had light shining, or a source of light that was just shining down right here, right? That was coming kind of from really high up. What would this point look like? What would the point 1, 2, 3 look like if it were projected onto the XY plane, right? So if this is you looking down, then this point looks the same as the point right here. So the projection is the point 1, comma, 2, comma, 0. Does that make sense? So remember, you're coming down 1, you're going to the right 2, and then you were going up 3. But now if we project it onto the xy plane, then that's the same as coming down 1, coming forward 1, going to the right 2, and then not moving at all, right? So z equal to 0. Now what happens if we project 1, comma, 2, comma, 3 onto the xz plane? So let's see here. So what happens if we project it onto the xz plane? Okay, so we said that we're coming, so you come down 1, you move up 2, and then you move, sorry, to the right 2, and then you move up 3. So this is 1, comma, 2, comma, 3. And then we're moving 3 up and down. And we want to project onto the xz plane. So I've got to figure out where is the xz plane. Do we remember where the xz plane is? The xz plane involves x and z, the x-axis and the z-axis. Okay. So now, if I were to project, so now imagine that your light source is back here. Okay. And now if you project this point onto the xz plane, it's like you're pushing it back to here. So what would you get? You need to move forward 1 and move up 3. Okay, so you would get 1, comma, 0, comma, 3. Move forward 1. You're not moving left and right because you want to stay within the xz plane. So your y coordinate is going to be 0, but you do need to move up 3 so that you have the same height that you did before. Okay. So the projection onto the xz plane is 1, comma, 0, comma, 3. And lastly, let's see what happens if we, what's the coordinate if we project this point 1, comma, 2, comma, 3 onto the yz plane. So onto the yz plane, so we're coming 1, 2, 3. Okay. So this is 1, comma, 2, comma, 3. And the yz plane involves the y-axis and the z-axis. So now if I wanted to project this point 1, comma, 2, comma, 3 onto the yz plane, I need to essentially push it back to here. So what would I do? I'm not coming forward or backwards. I'm just moving 2 to the right and then moving up 3. So I should get the projection to be 0 because I didn't move any forward or backward because I need to stay in the YZ plane. 2 to the right, and then 3 up. And now you would want your light source, if we're still thinking about it in terms of light sources. Your light source would be from here projecting towards the plane. So projecting towards the plane. What did we do to get to 1, comma, 2, comma, 3? We moved forward 2 to the right, forward 1 to the right 2, and then up 3. But if I want to push it back into this YZ plane, then I'm not going to move forward any. I'm going to stay at x equals 0, and I'm going to move to the right 2, and I'm going to move up 3. So we get 0 because you're not moving forward or backwards, 2 because you're moving to the right 2 units, and 3 because you're moving up 3 units. Okay. So now overall, I would like to say that R3 is what we call 3D space. And this is the set of points A, B, C, where A, B, and C are real numbers. Okay. And we call R3 the set of all ordered triples of real numbers. And the way we have defined this coordinate space is the 3D rectangular coordinate system. And so in a little later in the semester, we will discuss different coordinate systems, different three-dimensional coordinate systems, right? We'll talk about polar coordinate system, just like we did with when we were dealing with two dimensions and we had rectangular coordinates and polar coordinates. We'll have different coordinate systems, but for now we're just focusing on the rectangular coordinate system. Okay, so later we'll look at spherical and cylindrical, but right now we're just working on rectangular. And a tip is that it's often helpful to picture a 3D coordinate system in terms of a room. And so you think about where two walls meet. So if you think about a coordinate system in terms of a room, then the planes, the XY plane and the XZ plane and the YZ plane. Okay, so in terms of a room, the floor is the XY plane. Okay, and then the walls would be the XZ plane and the YZ plane. Okay, one of the walls will be XZ, one of the walls will be YZ, and where they all meet, that little corner would be the origin. So sometimes that's helpful, a helpful way to think about it. Let's talk about graphing equations in 3D space. So let's just look at what do the graphs of the following equations look like. So the question is, what do the graphs of the following equations look like? So the first equation is z equals 0. The second equation is z equals 3. The third equation is z equals -1. The fourth equation is y equals 5. The fifth equation is going to be y equals x. Okay. So now for z equals 0, that means we want all points x, y, z, where z, the z value, should be equal to 0. So now what do all points, if a point looks like this, x comma y comma 0, what does it look like? Well, if z is 0, that means that you have no height because you didn't move up and you didn't move down. So it's any point, these are going to be points actually within the xy plane. So this is the xy plane. Because if your z coordinate is equal to 0, then you must be in the xy plane. Okay, this is very similar to back in, let me just remind you. So back in 2D, remember when we had x and y and this was 2D? And we would ask the question, what does the line y equals 0 look like? Plot the line y equals 0. What does it look like? Well, if y equals 0, x can be anything. X can be anything, but y has to be 0. That means that you're on the x-axis, right? Here, if we're in 3D space and we've got x, y, and z is equal to 0, you have no height. That means you have to be within this 3D. You have to be within this xy plane. Okay, now, what about the next example here, which is z equals 3? So now, all of our points. So this is for z equals 3. We're looking at all points that look like this, x comma y comma 3. What would it mean if your y value is always, if your z value is always 3? That means that you're always 3 units.
It's 17:45.
Thank you. You're always 3 units above the xy plane. Okay, so for instance, 1 comma 1 comma 3, come out 1, go to the right 1, go up 3. 1 comma negative 1 comma 3 should be come out 1, go to the left 1, and go up 3. Negative 1 comma 7 comma 3. So then I would go back 1, go 7, but I'm going up 3. Do you see how all the time we're coming up 3? We're always 3 units above. So the graph is going to be a plane that is parallel to the xy plane. So it's the xy plane, but imagine lifting it 3 units up. So this distance here is 3 units. So what does the graph look like? It is a plane parallel to the xy plane, but it is 3 units above. Okay. What about z equals negative 1? Well, if we apply similar reasoning, then if we're always having negative 1 as our z value, that means that all of the points in the graph, all of the points that satisfy this equation are 1 unit below the xy plane. Okay, so this is going to be a plane parallel to xy plane, but it is 1 unit down. Now, what about y equals 5? Let's see here. So now this is going to be a little different. For y equals 5, so this is D. That means that our points x, y, z have to have y equal to 5. So let's think. So we could have 1 comma 5 comma 1. So move out 1, move forward 5, move to the right 5, and move up 1. We could have 1 comma 5 comma 0. So we can move out 1, 5, and then 0. So that's there. What about negative 1 comma 5 comma 6? Because the key is that the y value always has to be 5. So negative 1 means we need to move back 1. We still have to move out 5, and we're going to move up 6. What about negative 1, 5, 13? So move back 1, move out 5. We're going to move up 13. Okay, 3, 5, 0, 1, 2, 3, 5, 0. Do you see what's in common with all these points? They all have to be in this plane here. It's like there's a wall at the point of y equals 5. Do you get that? So y equals 5 is going to be a plane that is parallel to the xz plane. And it is 5 units to the right. So just to help, because I know this is new, the xz plane, remember, looks like that. Okay? So imagine that xz plane, but it's shifted right 5 units, and that the equation for that is y equals 5. Okay, the last thing we want to do is we want to look at what about y equals x. So this is our last example here. We want to look at y equals x. What do we have for y equals x? Okay, so if we want to plot y equals x, we're looking at points where the x and the y values have to be the same. The x and the y coordinates have to be the same. So for instance, we could have 1, 1, 1, 1, 1, 5, 1, 1, right, up, forward 1, right 1, a negative number, it could be negative. We could also have -1, -1, 3, which would be -1, and then to the left, and then up 3. Let's see here. What is the factor that's the same here? Z can be anything, right? X and Y have to be the same. So now let's imagine what happens. Here's a way to help us to think about this, because looking at the picture, it's not coming as easily, the idea of what the shape of this graph should be. So one way to think about this, and this is an approach that is very helpful, so I'm going to put a tip here. So a strategy to investigate functions of two variables is for investigating functions of two variables is to just change one variable at a time. So if we do that, what I'm going to do is I'm going to say, imagine if z is fixed. So if z is equal to 0, what are the points that satisfy y is equal to x? That means I've got anything that looks like x comma y comma 0. But x is equal to y, remember? So that means I'm talking about this line, x equals y, right? And z equals 0. But now I could also have this happen if z is equal to 1. So if z is equal to 1, then what are the points that are that satisfy x is equal to y? We'll have those same points, but we're just moving them, shifting them all up by 1 unit. So I'll get x is equal to y, and now z is equal to 1. And I can do the same thing, and if I keep doing this, I'm going to end up with a plane, right? It's going to be a plane, a two-dimensional plane, and it's going to be slanted kind of in a sense. So it is not. So it's this plane here is not parallel to any of the coordinate axes, but it is on top of the line y equals x. So does that make sense? So now just to help us to see what's going on here, I'm going to put in, this is the xz plane. This is the xy plane. And this is the yz plane. And so this x equals y plane is kind of bisecting, if you will, all three of the planes like that. Okay, so let's do some more practice. And the question is, which points satisfy x squared plus y squared equals 1 and z equals 3? Okay, what does the graph of these points look like? So here's my x, here's my y, and here's my z. Now I know that x squared plus y squared equals 1. This is referring to a circle in 2 space. So remember, if we were back in 2 space where we had x and y, x squared plus y squared equals 1 would be the unit circle, right? Now I need points x comma y comma z. And I know that z needs to be equal to 3. And I know that x squared plus y squared needs to equal 1. So I'm going to go up, move up to 3, because all of my points have a value of 3. So I'm looking at points that are of this form, x comma y comma 3. If the y value is always equal to 3, that means that these points have to lie in this plane here. And remember, what's the equation of this plane is going to be c equals 3. And I'm saying that x squared plus y squared needs to equal 1. Well, that's the same as this circle. Okay, so I'll have points like this point here, which would be 1. So I move out 1, comma 0, comma 3. And then this point here, which is 0, comma 1, comma 3. This point back here is -1, comma 0, comma 3. And then the point down here is -1, 0, comma -1, comma 3. Okay, so the answer is this is a circle that's lifted 3 units above the xy plane. So it's a circle 3 units above the xy plane. Okay, now let's ask the next question. What about which points satisfy x squared plus y squared equals 1? Now here, the answer depends on the context. So if you are working with 2 dimensions, then your answer is it's just going to be the unit circle. But since we're in 3D, since we're in 3-dimensional space, that means that we're considering points x, y, z. Now z can be anything, and we're saying that we need for x and y to just satisfy the relationship that x squared plus y squared is equal to 1. Okay, so if z can be anything, then look, if z is equal to 3, we got this circle that's lifted up 3 units high, right? And with if we think about, well, what if z is equal to 0, then we would have a circle that's not lifted up at all, right? If z is equal to 3, we've got a circle that is 3 units high. If z is equal to 6, we would have another circle 6 units high. Z could be -1, which means now our circle is is below the xy plane. And now what's the union of all these circles, right? So think about all the possible circles. What if z is equal to 1.5 or 2.736? All these circles give us a cylinder. Right? So it's, imagine a tube that's going forever, right? And now coming out. Does that make sense? So what's the graph of this cylinder? It is x squared plus y squared equals 1. Because notice, since z doesn't show up in the equation, that indicates that z can be anything, which means this cylinder is going to have infinite height, if you will, and infinite depth. Okay? All right, so we've got a question here. We're going to ask the question. The question is this. Imagine if you are 2 units below the xy plane. So let's see here. What point is 2 units below the xy plane? Well, actually, I need a little bit more information, right? Because there are many points that are 2 units below the xy plane. So add this condition, and you're in the yz plane. Okay, so let's think about this. So to start off, I'm going to sketch. Okay, so now we know the xy plane XY plane is this here, right? That's the XY plane. And the YZ plane
It's 18 hours.
and this is our YZ plane. Okay, so I want 2 units below the XY plane. So this is the XY plane, so I have to drop down 2 units. But I also want to be within the YZ plane. So within this YZ plane, which is like this, I need to be 2 units below. If I am in the YZ plane, that means that my X coordinate is 0. So this is what a typical point in the YZ plane. These are the coordinates of a typical point in the YZ plane. Now, what does it mean to be 2 units below the XY plane? If I am 2 units below the XY plane, that means that my Z value must be equal to -2. Okay, so I can adjust this even more to say that I'm looking at 0, y, -2. So 0, y can be anything, and then -2. I'm actually any point on this line here. Does that make sense? So I've got that little line that's an intersection. Like, think about this. The point 0, 1, -2. So 0, I'm going to go 1 and then -2. That's definitely in the YZ plane, and it's definitely 2 units below the XY plane. Right? But so is 0, 7, -2. So if 0, then if I go out 7 and then go down, right, I'm going to get a point that is definitely in the YZ plane because x is equal to 0, and it is 2 units below. Okay, so that's good. Now, the last thing that I want to talk about is we've talked about graphing equations in the 3D space. The last thing I want to talk about is distance. So we as a reminder, distance in 2 dimensions was this formula here, and it was based off of the Pythagorean Theorem. And we can do the same thing to find the distance between 2 points in 3 space. Okay, so if we have so here's x, here's y, here's z. So if we have 2 points in 3 space, let's say there are 2 points like this. What we could do is we could consider the box. Let's see here. What might be so let's see here. So say these coordinates were A, B, C. I think I need to choose points that will show it highlighted better. Okay. So suppose this is come out A, go over B, and then go up C. This is A, B, C. And now where do we get this point from? Come out X, let's say D, go up E, and then go up F. So this is D, E, F. What we can do is we can form a box where the edges, where these points are edges on the box. Does that make sense? So imagine we'll have a box so that this now is the hypotenuse of a triangle. Thank you. And this triangle is inside. This triangle, this is difficult. I should have put in a graphic to show. Okay, so what I'm going to do is I'm going to pause the video now, and I'm going to upload, I'll upload a second video that explains the distance formula. Or in fact, probably what I'll do is I'll just post a YouTube video. I'll find a good YouTube video because this video right here is going kind of long. We're already an hour into it. Okay, so I'll post a quick, short, cute YouTube video on the distance formula and the equation of a sphere. Okay? All right.